So you guys probably know a lot about blockchain, and you've definitely heard, a whole lot of jargon in the last couple modules. And what I want to do in this module is kind of build blockchain up from first principles, okay? So if you're pretty familiar, this will be like really nailing down the things that you've read in various white papers. And if you've had this feeling like, oh my God, I get game theory, I get cryptography, but like these guys seem to know so much blockchain, don't worry, because this is where we're going to build it all up, both through me talking at you, but also through a lot of hands-on activity and coding, things like that. Okay, so here we go. Let's talk about the goals of our blockchain systems. What are our goals? I like to think of it in two different ways. They're both totally compatible, but sort of different frameworks for looking at this. The first one, that's probably more prevalent and a little easier to wrap your mind around, is that we want to be able to trustlessly provision infrastructure. And what I mean by infrastructure in this case is basically like compute infrastructure in order to run the applications that we use every day. We want to disintermediate the server operators and not allow them to continue to abuse our privacy and other properties. What's up? No problem. Oh yeah, there's the mic. So the other way that maybe is a little less obvious and a little more abstract is that blockchain systems are really a way for us to coordinate with people all over the world who you might not trust, who you might not have any pre-existing relationship with, but who you might want to interact with for some reason. Maybe you want to buy or sell something to that person, or maybe you want to work together on some project. Maybe you want to vote, have some voting system where you don't have to trust the elections board to tell you the outcome. You want to be able to confirm it yourself. So what we're trying to build here basically is trustless ways for people to coordinate with each other. And it's going to get really technical, and I think that's good. So let me make an analogy to crypto, because you guys all did crypto last week. So cryptography provides really strong and hard guarantees, mathematical kinds of guarantees about messages, like DMs or something. If I want to send you an email or a DM, I can send it to you with cryptography, and then you have all these guarantees. Like somebody yell out, like what were one of the guarantees if I send you like a signed encrypted message? What do you know about it? Yell it out really loud, I didn't hear you. Yep, non-repudiation, okay, yep. What's another one? Integrity, yep.
Authenticity.
Yep, good. Yeah, you guys are killing it, that's awesome. So we want to have these kind of same strong guarantees, not only about sending messages across a wire, but about whole complex systems that we operate with, like a currency system or a political system or something like that. All right, so before we get to Web3, let's do a little trip down memory lane of all the different iterations of the web. I don't know of anyone else who uses the term Web 0, but I like it, and I hope you'll all try to make it spread, because I think it's intuitive. So when I say Web 0, I'm talking about before there really was an internet, when we first started experimenting with communications across long distances. And in this Web 0 era, you had things like the telegraph or the telephone. You basically had like maybe me on one end holding my telephone, and there's just a long wire, maybe routed across the country or something like that, and then on the other end is your telephone. And there's probably some switchboards in the middle because you're not always calling the same person. Is this thing, what's going on here? Is the volume inconsistent? Hello. Oh, okay, all right. Maybe it's just, yeah. So in Web 0, we didn't typically use cryptography, except maybe by the military or other people who had like particularly specific threat models. But we should have, and we could have. This is a classic example of where you can use cryptography. You can't, too closer? What do you mean, like this? 0 degrees like this? Is it better? Yeah, it does seem better. All right, I'm gonna hit the gym tomorrow so I can keep up all week. Okay, so my point here is that apart from maybe some switchboard operators who help you set up this connection, you basically have a wire end-to-end, and that's a perfect opportunity to use cryptography. So let's switch over to Web 1 here. This is where we have an introduction of an always-on server. Previously, when you're dealing with something like this, you're not expecting a human to be sitting by the phone all the time, right? It's like an on-demand kind of thing. But with Web 1, now we have this server that's always on the internet. So I've kind of drawn it here. You have like a couple of servers sitting around. These guys are always online. And then you have users who connect to those servers. And what I've done here is I've kind of used pink lines to indicate like this is my server. So this lady up here like has her server. And what she might do with this server is like maybe she's a scientist, maybe she's a chemist. And she's about to publish some new paper about her uncertainty principle, and she wants all of her colleagues to read it, but she doesn't want to be sitting there on the phone constantly telling it to everybody, so she publishes it on her server, and then anyone else can get it anytime they want. And so you can see, like, with green lines, other people connecting to this lady's server. And some people might not have their own server at all. They might just be casual users. And maybe this is like a corporate server or like a university server where you can see there's like a whole bunch of different people on it. So just kind of sketching out like topology here. So this is still mostly peer-to-peer. In some sense, people kind of have their own servers, or at least some approximation of that. And people did use cryptography sometimes, but not as often. And I think it's mostly, again, just the case that like the threat model wasn't there. People didn't know yet that you can extract so much value on the internet, and they weren't worried about getting ripped off. But the other thing I think is that Web 1 had a really different use case. It was basically for publishing, like I said, and sharing data sets and things like that. And so when you're trying to publish something and make it public, you definitely don't need encryption, right? That's when you need secrecy, when you want it to not be public. But a really good thing we could have done in Web 1 was sign our papers. This would be a great use for digital signatures. When Alice here wants to publish her uncertainty principle paper, she can sign it, and then everybody knows, like, oh, this thing really is from Alice, not someone who's just trying to like capitalize on her reputation as a good scientist. Okay, so I think of Web 1 as a small iteration on top of Web 0, where we're starting to experiment with always being on and things like that. So Web 2 is where the Web 2 is where the revolution really starts. So with Web 2, it's not just about publishing my data set or like reading this poem that I wrote or whatever. With Web 2, we start to actually have like applications. You can have something like MySpace or Facebook, or like as an example, the state of Ohio, where I'm from, has their BMV, their Bureau of Motor Vehicles, online. You can like renew your automobile registration or something on the internet. And so this is kind of the beginning of Web 2, and now it's always really administered by some kind of service provider. Like the service has to run on some kind of server, and so here in my example, you can see I have like the Facebook server, and all of the users are connecting directly to it. So what is like conspicuously missing from the diagram this time? Can anyone see it? Yeah, the pink lines, that's right. Yeah, and it's not peer-to-peer anymore, that's right. Everybody has a central point of failure here, okay? So what can happen in these kinds of services, I mean, I'm sure you guys have thought about it already, but like maybe Alice posts some post on Facebook, and Facebook doesn't like that post, so Facebook posts something different instead, and none of the other peers are able to tell that. And even if you use a service that has like HTTPS, right? That's good. You've got that little lock symbol in your browser bar. It makes you feel nice and secure. It is good. You do want to look for that. But remember the implications here. If Alice sees an HTTPS lock on the Facebook website, that means she's communicating securely with Facebook. She has these strong cryptographic guarantees with Facebook. Facebook knows that the messages are really from Alice, and Alice knows that what she's seeing is really from Facebook. And each person has that same relationship with Facebook. But no one has that same relationship with each other. There's always an intermediary who can be really nasty. And I'm not trying to say that any particular intermediary is nasty or is inherently nasty. In fact, it could be quite nice. Maybe you think that Facebook's doing an awesome job and is really being benevolent. That doesn't eliminate the threat model. That doesn't change the fact that any day the service provider could have a change of heart and change the terms under which you're using their service. And so that's what we're trying to take care of. Yeah, I guess I pretty much talked through this one already, didn't I? All right, so let's do a trust example here. Wow, did I talk through this one too? So we've got 2 users on Twitter, and when you're using Twitter, you tend to trust that what you're seeing is, we're all seeing information from the same database. And what I mean is, when I go to Twitter and load up some particular tweet, and then you go to Twitter and load up that same tweet, what we expect is that we're all seeing the same tweet, not that the server is like equivocating or telling different, inconsistent information to different people. Yeah, and for example, if I see that, oh, this tweet is from Andrew, I trust that that actually was from Andrew, not that, oh, Jonas wrote this, and now Facebook is trying to convince me that Andrew believes the same thing as Jonas. That's something that they could do as an intermediary. And we want to restore this trust, and we have tools like digital signatures to use it. So let me just foreshadow a little bit. What we're going to do in this module is we're going to try to glue together these rich apps, these digital services that you see in a Web 2 environment, and we're going to try to glue them together with these strong guarantees that we get from cryptography. So that's our general technique that we're undergoing. Yeah, question. Where's the mic? Chuck it over there. Here it goes. Go ahead.
In the previous slide, the reach state was in bold, or the one before that.
Is this the one? No, before that.
Yeah.
What do I mean by state? Is that what you're saying?
Yeah, I mean, it was in bold, and you didn't.
Yeah. I probably should be clear what that means. So when I'm talking about state, I'm talking about all of the information that you expect, like the Facebook server, for example, to be tracking for you. So basically, like all of your posts and all of everybody's posts and all of your comments and all of your likes and your profile picture and all of that stuff. Basically, by state, I mean any content that's in this service, that's managed by this service. So to give you another example, if this were like my bank's server, then the rich state would be like all of me and everybody other users' account balances and debts and all, all of that kind of stuff. Or if this is the BMV, this would be like all of our car registrations and maybe our like history of citations or something like that.
So in this context, rich means like big, vast?
Yeah, and it means that it can be big and vast, or it can be tiny. It means that it can be like a really complex data structure, or it can be an integer. Rich basically means like flexible. We're not trying to prescribe any one thing. So I've given you these examples of like Facebook and my bank and a car registry, and those are like pretty significantly different things. And so that's what I mean by rich. We can model a lot of systems this way. Yeah, okay, so in Web 2, service providers can perform lots of abuses. They can censor us, they can restrict us from interacting either entirely or with particular users or in particular ways. They can also just fail to produce requested data. Maybe you say, hey, let me see this tweet that used to be here, and they'll say, this tweet violated our terms of service, or this tweet was deleted by the user. Or maybe the page just doesn't load, and it seems like, maybe their service is down, I'll try again later, and maybe you don't get back to it. So service providers have lots of ways to sort of like be sneaky, but the worst one is this. You don't really know, you don't have any way to know what state is supposed to be inside of Facebook. You don't have any way to know what posts people sent to Facebook. All you know is what Facebook tells you is there. And therefore they can switch the state and change it around behind the scenes without anyone knowing. So these are the things we're trying to guard against. Now you guys probably know, or let's just see if you know. What was the first application of blockchain that we heard of? What? Oh, okay, so Napster's not a blockchain, but it is a peer-to-peer network. And yeah, it's definitely in the history that we're talking about here, yeah. So yeah, another great P2P network. Yeah, BitTorrent, yes, exactly. Still not a blockchain, but again, very much in the right way. So the first blockchain I think of is the Bitcoin one. And it is, is it social media? No, not really. Is it a motor vehicle registration? No, it's a cryptocurrency, or a currency, I should say, a digital currency. Okay, so let me ask you this question. So Bitcoin came out and people were like, oh, wow, this is new, this is novel. So is a currency this notion of like, I have some balance and you have some balance and you have some balance? Or maybe you can think of it as like, there's a whole bunch of coins out there and everybody owns, each coin has some owner.
It's a ledger.
Hand ups. Go ahead. Say it again.
It's a ledger.
Yeah, it's a ledger. That's right. So here's my question. Here's the thought experiment. Could you build something like that in Web 2 where like I have a balance and I can send some token? I click the send button and who I want to go to. This guy's nodding. You could do that, right? Did anybody take like intro to React or web apps or anything like that? This is exactly the kind of thing that you might build as like, an assignment in an undergrad course. So the thing that's novel about Bitcoin is not cryptocurrency. What's novel about it is the ledger, the shared history, the opaqueness, and the immutability of it. And so we're going to see how this is built in Web3. I do want to give. I don't know what that is. Oh yeah, watch out for the cubes. Okay, so I do want to give credit where it's due. Web 2 is not entirely centralized in all the worst ways. Most service providers want to keep their services online. Facebook doesn't want to go down. Amazon doesn't want to go down. They want to stay up. And so they are distributed in many ways, like geographically and politically. So for example, if all of a company's servers are in California and then there's an earthquake, the service could go completely offline. But if they have other servers here in Hong Kong and others up in Europe and Australia, then when there's an earthquake in California, they can survive. And so this is good. And this is something we actually want to copy from Web 2. For example, having our big blockchain nodes all over the world. But it's not enough. That's the point. This is not enough, and we can do better. So in Web 3, what we're trying to do is provision these digital services without needing to trust the service provider. And so instead of trusting them, instead of trying to establish some trust relation somehow, we want to use all these tools that Jonas taught us, these economic and game theoretic tools, to actually incentivize the service providers to operate the way we want to. So it's no longer like, oh, service provider, please be honest. We love your platform. Please don't screw us. Now it's like, if the service provider wants to get ahead, the way that they can get ahead the most is by behaving honestly, by running an honest Facebook or an honest Amazon. And then we want to allow all of the users to interact with this system without having to trust anybody, including intermediaries, not only the service provider, without trusting any intermediaries. Okay, let me pause. Any comments or thoughts? Okay, yeah, let's roll. That's great. So I'm going to go through some desired properties here. I'm going to do them pretty fast because we've talked about them a little bit. Permissionless access. We want anyone to be able to use the system. Not just rich people, not just people who live in Hong Kong, not just people who are friends with the right others. We want anybody to be able to use our systems. We want privacy. We don't want everybody to know how much money we have or who we're voting for or how many cars we have registered or what we post on Facebook. Well, maybe that one's a little different. But the point is we want to be able to have privacy when we need it. We don't want to be uncertain about what information is being collected and who it's being gossiped to. For example, the government or your enemy country's government or whoever you don't trust. The NSA, if you're an American, watch out for them. Well, the NSA if you're anyone, really. Okay, authenticity. This one's basically the same as in cryptography. We want to know who sent these messages and have ways to know that they're authentic. And finality is a new one. So finality means when I register my motor vehicle, I want some guarantee that this thing is going to be processed in some kind of time. Or at least I want to know that once it's been processed, they're never going to change their mind and arbitrarily revert my registration. Now, it doesn't mean it can't be banned if I get in an accident or drive recklessly or something. It just means that they can't go back and change history and say, oh, we never gave you a registration in the first place. So I, as someone who's registering my vehicle, I want to know that once its registration's in there, it's in there. And I want to be able to prove that to anyone. So for example, if I get pulled over by a cop and I suspect the cop is corrupt or trying to frame me, and he or she says, or they say you don't have a registration, I should be able to, using only math, say, no, here is my registration. It's proven. It's shown that I registered, maybe by signature from the BMV or something. We want to guarantee that our systems behave the way we expect. And here's the interesting caveat here. Obviously, we want our systems to behave the way we expect. We want the system as a whole to perform the way we expect, even when individual server operators or service providers don't behave the way we expect. So let's say we decentralize Twitter. We now have 100 Twitter nodes around the world. And let's say one of them is malicious and tries to pull the old usual tricks or censor someone. We want to be sure that even when that 1% of the Twitter operators is misbehaving, Twitter as a whole, or the service as a whole, still upholds its guarantees. Now, what we're going to see is that there's usually some threshold. You can tolerate some percentage of operators acting badly, and maybe even a lower threshold if they're kind of coordinating. And that's good, or we can choose the threshold that's good enough, but we want it to be the case that no individual operator can, here's this one. No individual actor, company, state, or coalition should be able to degrade these properties. So that's what we want. All right, so in this talk, I'm going to go a little bit philosophical, and then I'm going to go technical, okay? Who's read it? Yeah, this is a good book. This is one of my favorites. If you're a reader, please read it. This is the history of our species, or at least this one person's perspective on it. Now that we understand these goals in Web3, we got to talk about how we achieve them. So the key is allowing all of the users to agree on a shared history. So wrap your head around that. This is my claim, okay? This is one of my theses for this module. The key idea here is that we're going to allow users to have all of these great properties, unstoppable apps, privacy, blah, 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 by allowing them to agree on a shared history. So here's a quote from that book. Any large-scale operation, whether it's a modern country, a medieval church, or even some archaic tribe, is rooted in common stories that exist only in people's collective imaginations. Telling these stories isn't easy. The difficulty lies in convincing everyone to believe it. Much of history revolves around this question. How does one convince millions of people to believe their particular stories about gods, nations, or LLCs? This is what we're going to try to answer here. Okay, so Harari in his book argues that getting people to believe shared histories, shared myths, shared stories is what's gotten us as far as we have as humans, and I'm here to argue that blockchain is the next iteration in this journey. All right, we got to figure that out. Where's the mics? Hold up the mic if you have one.
It's trying to be fixed.
Oh, got it. You're working on it. Okay, nice. Was that it? Did you solve it?
I'm trying to figure it out.
Oh, nice. All right, great job. Thank you. Oops. Whoa. Spoilers. So this is what we're going to do, okay? We're setting out to solve this problem, the problem of human history. And here's how we're going to do it. I'm going to introduce this mathematical formalization, and it's called a state machine. And the way a state machine works is that it has a bunch of states, usually a finite set of states, but it can also be an infinite set of states. And then you can perform state transitions. So you start out in some initial state, then you have some transition, and you end up in some final state. So what you see here on the screen is like a very short history of some state machine. It's very short because only one thing happened. You know, it was like once upon a time, state one, and then one thing happened, and then we were in state two, and the end. Maybe we lived happily ever after. But you can imagine that this history can grow quite long. And so, for example, Bitcoin is a state machine. The currency is the state machine. Or in the examples I gave earlier, a much more complex one would be like Twitter as a state machine. And one way that we can sort of draw out a state machine is as a labeled transition system. This works for small ones. I mean, in theory, it works for all of them, but like you don't want to do it exhaustively on big ones. So drawing out all of the states, what I've done here is like A, B, C, and D are states, and then 1, 2, 3, 4, and 5 are transitions that you can make. So when you're designing a state machine, this is how you define it. You define all of your states, the pink boxes, and all of the transitions that you can make between those states, which are the purple arrows. So without even explaining it any further, if I'm in state C, and then I have a transition type 4, what state am I in next? D. Yeah, bingo. Okay, so if I'm in state D, and then I have a transition type 1, what state am I in? Yeah, that doesn't make any sense, right? Because there is no transition type 1 coming out of D. Yeah, Marcus here.
So, I think we're going to maybe talk about this later, but this kind of looks like a graph in essence, more or less. Are we going to get more into graph theory?
I love graph theory, and this is a graph. In a graph, you have nodes, which are the states, and edges, which connect them, which are my arrows. And in this particular graph, it's a directed graph. That means it has the arrows on the line. So if I only had lines, it would be a non-directed graph. It's going to come up over and over. I'm never going to do a formal lesson on graph theory, but it's going to come up a lot. And thank you for bringing it up. This is indeed a graph, and it's a directed graph. It's actually, to be even more specific, it's a cyclic directed graph because we have a cycle right here, and we also have a big cycle around the outside. Not all graphs are cyclic. Some are called acyclic, and those ones are really interesting too. Okay, so I have an example. A light switch and the light that goes with it. It has two states, either on or off, and it has a single type of transition, which is called toggle. Okay, so maybe you can think of this actually as like a light button, you know, not a switch. So if it's on and you push the button, then it goes off. If it's off, you push the button, goes back to on. Very simple state machine, okay? And it also illustrates the point that wasn't in my previous example. Here, there's only a type 1 transition here, okay? I only have a single type 1 transition. It isn't always that way though. In my later one, you can see that both of these transitions are toggle, okay? So you can reuse your transitions wherever you need them when you're modeling your state system. So here's a question for you guys and another example that I want to do. It's an audio amplifier, okay? In fact, we have one right here, but the one we're going to model is a simpler audio amplifier, okay? Imagine there's like an input that goes maybe to your TV or computer or microphone or whatever, and then there's an output that goes to some speaker, and the control panel that we're using on our audio amplifier has 3 buttons, okay? It has a button that says louder, a button that says quieter, and a button that says mute. And then let me tell you our states here as well. So there's 4 states, and the 4 states that the audio amplifier can be in are silent, which means, no noise at all. Quiet, which is like and then normal and loud. Okay, so there's silent, quiet, normal, and loud. And so basically, I haven't fully defined it because I'm hoping you can intuit kind of how this thing works. Like if it's in, quiet and you press louder, then it goes up to normal. And if you press louder again, it goes up to loud. And if you press quieter, it goes back to normal. And if you press mute, it goes to silent. And then if you press mute again, it goes back to wherever it was before. So what I want you guys to do is spend 5 minutes with your people nearby you, or if you hate those people, then go find other people. And grab a piece of paper or whatever, if you have a iPad or tablet, and try to draw out something like this. And you'll end up labeling your pink boxes like, silent, loud, whatever they are, and your arrows will be the 3 buttons, mute, louder, and quieter. And we'll discuss it in a few minutes. I like the way you're thinking. Yes, great. I love it. I love the way you're thinking. Yep, see if you can solve it.
Tenemos 4 estados. Tenemos el estado silent, el estado ¿cómo era? Quiet, el estado normal y el estado louder. Tienen 4 estados. Tenemos las state transition functions, que son apretar silent, apretar, vamos a volver a explicar mejor, apretar silent, apretar quieter, apretar entonces, cualquiera de estos va a silent.
Does anybody want to share their states? And feel free to keep talking. I'm not trying to stop you. We can go at the same time. Anybody want to yell out their states? Okay, that's a good start. What kind of states?
Porque la idea es que si vos vas a silent, después tenés que saber, digamos, a cuál volver. Si vos tenés un amplificador y lo querés mutear, cuando lo desmutees, querés que vuelva al volumen que tenían como lateral. Entonces por eso tenés que guardar, digamos, el mute state. Y entonces después, según el preview, ahora vamos a hacer las flechitas para que queden bien. Esta parte es muy fácil, digamos. Esto va así. Y esto va así. Esta parte es fácil. Pero
Unmuting is the hardest part. Unmuting is hard, so think that through carefully.
if we're on quiet, and so we press quieter, we go to silent.
Yes.
Yeah. So this
What does it say in parens down there?
previous state because you have to add storage.
Ah, okay. Okay. Very interesting. Very interesting.
Esta también. Va acá. Y ahora, ¿cómo volvemos a silent? A quiet. Entonces, si se presiona silent de vuelta, si se presiona louder, tenemos que volver acá. Acá tenés. Si se presiona esto también. de que se entienda.
Wow, I love the enthusiasm. Okay, I can't go to everybody. I love how hard you guys worked. Let's start talking through it. I saw a lot of people starting like this. And I'm okay with a little noise as people boil down, just in case you guys are worried. So a lot of people started with their states being exactly the output levels. And that's a great place to start. That's a very intuitive place to start. Let's see if it works. So there's silent, quiet, normal, and loud. All right, so let's draw some easy transitions in here. If I'm in silent and I press like louder, what happens? Yeah, okay, so these are pretty easy ones, right? I'm just gonna use plus, I guess. Oops. Okay, and then we can, what if I'm in like normal and I press minus, then what happens? Yeah, so these are the pretty straightforward ones. So far we're modeling this just right. Okay, couple edge cases. What if I'm in silent and I say quieter? Yeah, very good. So the way we show that is like this. It's just a little cycle there. You started in silent, you press the quieter button, you're still in silent. It doesn't get any quieter than that. So, you know, probably infer we can do the same thing over here. But now we get to the hardest part. So, what if I'm in normal and I press the mute button? Where do I go? Silent, okay. That seems pretty good. I'll label this as M. And now what if I'm in silent and I press mute button again? Now where do I go?
You don't know.
Oh, yeah, some people are saying silent. Okay, this is actually a pretty interesting idea that maybe I didn't explain clearly enough. This is a perfectly valid state machine, but this actually isn't what I was trying to design. What I want to happen is if I'm in normal and I press mute, the thing gets silent. But then if I press mute again, that like toggles it. So I should go back to wherever I was before.
So you have to have one silent for each transition that you made.
Interesting.
Different silent.
Interesting.
For the silent.
Yeah, so I think that's right. I don't think we can solve it with only 4 states. It's actually a little more complex than I had let on. Here, maybe I'll let everybody take a peek. So let me try this. Let's see if this idea works. Let's add some more states. I'm going to get rid of these mute ones, okay, because we decided we're not ready to model mute with these states. So I'm going to add some more here. And I'll call this quiet, muted. All right, and then I'll make another state down here that's called normal, but muted. And then one down here that's called loud, but muted, okay? And so now that I'm duplicating these states, that's actually great news. Because I can use these states, instead of just having one silent one, I have separate ones in order to track where I came from before I muted this thing. So we'll leave this one up top as a single one that is like silent with, you got here not by muting. So if you're in this silent and you mute, then sure, you can stay here. Mute does nothing. It toggles you back and forth between silent. But what if I'm in normal and I mute? Then where do I go? Yep. Okay, yep, and then we can unmute the same way, all right. I'll stop rating the M's, I'll just use blue. All right, so this is pretty good, but you know, now we have to do our green and red transitions over here. So I didn't fully specify what should happen, but what is like one reasonable thing that could happen? If I'm in normal muted and then I press quieter, what might happen? I heard like 3 different things and they were all good. There's not one that's correct. It's just a matter of like, what system are we modeling? How do we actually want this amplifier to work? One was that if you're muted, the quiet button doesn't do anything. So you could just, oh yeah, well, okay, let's do loud, you're right. You could just stay here. That's one thing that people said. That's fine. Another thing that you could do is say, if you're muted and you press any volume button at all, maybe that means you want to hear some sound. So maybe we can, do something like this. Yeah, we'll get a little quieter, like you said, and also unmute. It's a reasonable thing to do. Or maybe we could say, like, it stays muted. You're already muted. Pressing quieter when you're muted shouldn't make noise come out. Maybe we just go down to here, okay? So, oh, whoops. Sorry, I'm getting a little, they go this way. Okay, so I think if this were like an assignment, obviously I would need to specify exactly how do I want this amplifier to work. But it's not, it's just a discussion. So I hope that this was like useful for understanding state transition systems. Does anyone want to ask anything about either label transition systems or state machines in general? Yeah, hock the mic back here by the camera. Right, throw that mic, guys. Throw that into the back by the camera. Go ahead.
Can we, like, in the current state, can we have like additional variables which are part of the state? So in the silent one, we know how we got to silent.
That's a great idea. Yeah. So the way that I've drawn this here is sort of, you can call it like the fully explicit state machine, where I've drawn literally every single state as a separate box. A common thing to do is to say like, okay, there's a lot of duplication. Maybe I can kind of like invent some notation to condense this a little bit, and then you put like internal state or fields inside of here. Great idea, great thing to do. Yep. I would say this is sort of the fully like rigorous way to think of it, and that's the much more practical way to think of it. Mike. Go ahead.
Yeah, like that's the solution that we did, but in a sense, it is, like you said, like to describe it like that would be like an abstraction of it.
Yeah.
But actually, the states are stateless. You could say the states.
Yeah. That's exactly.
So, like,
right.
if you have, for example, silent plus another data field saying "How did I get here?" then
like
eventually,
a previous
it's
state.
when you like compile it down or whatever, then you do have this at the end.
Yeah, and when you're writing your blockchain systems, it's going to be a lot more like what you described, because they're going to have hundreds or thousands or infinitely many states. So, all right, very good. Oh yeah, and so okay. These are 2 different graphs that are showing 2 different things. The top one is the labeled transition system for my light switch. This is what you guys just did for the audio amplifier. The bottom, although I used similar notation, is a totally different thing. This is the history of the system. And this history is a one-way thing. It always grows, always grows. And so, in this simple system, the only way it could ever look is toggle off, toggle on. But this is basically how we track the history of a state machine. Okay, so here's another example of a state machine. This one's called digital cache. Oh, and actually, I'm using your notation here already on this one, so I'm glad you brought that up.
Excuse me. Hey,
Oh, question, go ahead. Or
in
comment
the
or something.
previous state machine, how do you put mode? I don't need the explicit states, but I just need mode, that in case.
I didn't hear one critical word. How do you put what?
Mode.
Mode.
Yeah. So
M-O-D-E?
yes, please. Like the one saying that you can have volume up and down in mute, but it will not do anything. And in the other, if you touch anything in the volume down, then it will basically let the speakers on, but at a lesser volume.
Are you talking about like these ones here where you're in silent and you say get quieter and you still end up right back where you were?
Yeah, this one. Or if you are in silent and you originally came from normal, right?
By muting? There's no transition that goes from normal directly to silent.
Not in your graph, but there would be, right? Like if you mute. So
I have a separate state for that.
You may not need it, but let's say you have it, then in case...
You do certainly need it. We tried to do it with only 4 states and we found that you couldn't do it. Now, you might be saying like, I don't like this fully explicit notation.
Yeah.
It's too much. And that's exactly what he was describing, and it's exactly what I'm
Yeah.
going to show you here. Thank you for asking. That's a great comment.
But how do you...
Let's talk about it more afterwards, though. I want to just
Okay.
keep rolling so we can finish by lunch. Thank you very much. Oh, wait, did I finish that one? No, I didn't even do this one. Okay, so this is called digital cash, okay? This is very similar to Bitcoin. And I want to just like pause and like kind of give you guys all a wink here And the wink means this slide is going to be more important than it typically would be because it's relevant to your assignment this time. So pay attention to this one. So the state here is a complete set of banknotes, okay? It can be a lot of them. In this case, it's only 2. Or by banknotes, I mean like, you know, like dollar bills or something. Or you can think of it like coins. And so let's see what I say. So each one of the coins has an amount. So this is like a $5 coin, and it has a person who owns it, like so Alice in this case. And then the transition involves a user consuming or spending some banknotes and creating new ones, okay? So there's no like, I'm Alice with a $5 bill, and I'm about to buy a $2 coffee, so I'm gonna like rip my bill at the 2/5 mark. That's not how it works. You give away the $5 bill in entirety, and then there's change, okay? So that's how digital cash works, same as normal cash. You don't go around ripping the bills and coins. And so what kind of state transition, this is a spend, obviously, but there's more details about what the spend was. So can you infer from the 2 states, like what was that state transition? Who spent, what coins moved, etc.?
Transfer?
That's good. We're all getting used to the setup here. Definitely coins were transferred. Yep, that's absolutely right. But which ones? Which one of these was consumed? The top one, Alice's. Yep. And a new one was created. And the bottom one didn't change at all. So typically what happens when you're spending is you choose some of these things, destroy them completely, and then you add some new ones in over here. And so what we can see is that Alice basically paid $5 to Bob. Now this note is a $5 note owned by Bob. Cool. This is a foreshadowing of what we're going to call the UTXO model later on. But for now, we're just calling it digital cash.
In that model, can we say node 1 is burned and another node which is owned by Bob is created?
Oh, sorry, say it again. Note 1 is burned. That's right. What was the second part?
Burned and minted. Can we use this?
Yes, exactly. So what happens here? In fact, I probably should have called this one like Note 3 or something. It was probably a little sloppy to call it the same name because it's a different new one, right? Like we totally got rid of this one and created a new one. Yep, that's how it works. And there should be some constraints too. Like I can't just burn whatever ones I want and mint arbitrarily new ones. You always have to like conserve the money, or else it's not a very good money system. Yeah, very good thinking. I feel like we've done a lot of examples. I'm going to skip this one. You guys can look at it when you're ready. Okay, so here are a couple more state machine examples. I want each of you guys to either pick one of these or pick something that is inspiring to you of your own brain and try to model the state machine again. Now, these are quite a bit more complex than our little audio amplifier, so you probably won't be able to write out all of the states unless you say like maybe there's only 3 voters and 2 alternatives, or if you say like our blackjack table uses a like very much reduced deck or something. So what I want you guys to do is just take a moment, write out like what would the states be? Let's say you choose ride-sharing platform. What would the states be? What would the transitions be? And then maybe start to sketch out a graph like this, okay? So let's take like 5 to 10 minutes for that one.
Wait, okay.
So in the vote, we have I vote, maybe I vote for GMO. So the state is not the state is candidate. So probably like this candidate, and we can also expand it to like this candidate has this many votes and first priority. That if transition would be
Okay, yeah, good. You're thinking through it. So you're doing the ride sharing one, I guess, right? So if let's maybe start modeling it pretty simple. Let's say there's like one driver and like one person, okay? And then the only way that you can interact with that is like as a passenger, you can like request a ride and then get out of the car and then like get out. So I think in that case your states would be like the passengers in the car as a state, or the passengers like not requesting a ride or anything, just content, not really using it, or the passengers like waiting. So you can say like you're waiting. Maybe you say this. You're in the state of like content, and then you make the transition of request a ride, and then you're in the state of waiting, and then like you make the transition of like the ride arrives, and then you're in the state of like in the car or something like that. Yeah, exactly. And so like sometimes when you approach a new state machine, it's like pretty hard to model the whole thing like from first principles. So sometimes you can think of like, let's just imagine using this thing, like what's one path we might take. So maybe before we draw like our whole amplifier thing, we just think about simple ones. Like, what if I'm just like pressing louder, louder, quieter, quieter? That's like a pretty intuitive one, and then you can kind of build up the system. So what you're modeling here is more of a person moving around a space kind of state machine, which is a perfectly valid thing to do. So you could say like he's at point A, then he like walks north, then he's at point B, then he walks east. Yeah, that's also. Yeah. I mean, well, if you're in the terms of state machines in general, yes, there's a huge number of state machines there. For like, well, specifically for a ride-sharing platform, then the space of your states is kind of constrained. It could be. I sort of described it as a simpler one, but you could have a richer state space where it's like riders waiting at point, and then requests a ride at point C. It depends how thoroughly you want to model this.
I want to go to the side, but if I don't get it.
All right, let's call it back here. Who modeled blackjack table? You tried? Yeah, well, yeah, this was not really enough time to fully model a blackjack table. You guys did too? Would you say you did better than tried, or how'd you do? All right, hey guys, chuck that mic over there, and then tell me some of your states. No problem. That's how you know who's listening. I know.
It's working? Hello? Okay.
Yeah, go ahead. What are your states for blackjack? Tell me.
So we have 3 states. One is in progress, one is win, and one is bust. And then there are 3 different types of hit. So if you hit and it's over 21, you go bust. If it's hit equal 21, you win. And then if you hit and it's less than 21, you're just back in progress.
Okay, cool, yeah. That models very important aspects of the game. Very nice.
And then you have like the stay, which is if you stay and you're less than the dealer, you go bust. If you're over the dealer, you win. And if you're
Yep, very nice. Okay. Yeah, and I didn't realize it until you said this actually. You could think of this almost as a little bit of a non-deterministic state machine, because if I have like 11 and I hit, I don't know yet what state I'm going to end up in, So one way you can model that is with like hit ace, hit 2, hit 3. But it kind of isn't really true to the game, because as a game player, you're not choosing what card you're going to hit. That would be way too easy. You'd win every time. You're kind of relying on some randomness. Okay, very good. I talked to these guys over here about a ride-sharing system. They did very good too, but we're going to keep moving just to wrap this up for lunch. Okay, this is where it gets real. We know about state machines now. If we agree on the starting state, aka the genesis state, so maybe that's like silent for our amplifier, and we agree on the history of transitions, then we absolutely must agree on the current state. this. If you need to move it, you can. So this is actually the crux of what the blockchain is going to do for us. The blockchain is going to help us know a starting state, or actually it's more like we're going to choose a starting state when we launch a blockchain. And the blockchain is going to help us track the history of transitions. And from that, we're all going to agree on the current state. So if you take this back to Harari's quote about how a lot of the difficulties and a lot of the striving that humans have done over the history of our species is getting each other to agree to and believe in the same stories, this is what we're going to do. Our story is going to be a list of state transitions of a particular state machine. And let's just see how it works. Actually, we're going to see in detail how it works after lunch. Sorry for the tease. But let's talk about blockchains here. So there's sort of three aspects. If you look at any blockchain, maybe you let's say we pick one out of the hat. Oh, hey, we got Ethereum. Okay, or hey, we got Near, or whatever it is. You can always categorize them according to these three, or you not maybe categories, but like think about these three aspects of them. So the first one is the state machine, okay? We talked about that in this lesson. You guys get state machines now, okay? We'll keep using them, but there's not really much more we're going to introduce in state machines themselves. The second part is the shared history, okay? This is what the blockchain data structure does. This is what we're going to talk about after lunch. That's sort of the main thing in the module. And then the last thing is consensus. Once we have a history of a system, somehow we need to decide which one is the real one. Which of the many possible histories is the one that we all agree on? So for example, if you think of our amplifier, maybe I buy an amplifier and I press louder, louder, quieter, louder, quieter. But then someone else buys an amplifier and they press mute, 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 mute. Those are all valid, both valid histories of our amplifier. But if our amplifier is something like a voting system, then we need to all agree on which one is the real one. When we don't all have our private amplifier, when we have a single shared voting system, we all have to be on the same page about which one's the real one. And just to tie this like very concretely to the real world, we're being kind of academic and technical about it here, but this is actually the problem always. We're trying to decide when the electorate board says, candidate A won the election, whether that's true. And when someone says, you know, this is false, we actually don't agree who all voted and what the votes were. We have to decide on a history. And so we've been doing this all along through human history, and now we're introducing mathematical tools and computer science tools to help us do it more formally and have better like understanding and transparency into the systems that we all rely on. So let's just look through a short history of them. Oh, this picture is right from the Bitcoin white paper. It shows a transaction. It actually shows the same kind of transaction I talked about earlier from the digital cash system. So in a spend transaction, you basically can input some certain coins and then you output some new ones into the next state. This is called the unspent transaction model, like I said. That's its state machine, by the way. Its state machine is called the UTXO model, cryptocurrency UTXO model. Its consensus is called proof of work. We're going to talk a lot about consensus later this week. Both Andrew and I have a lesson on consensus. Only a few years after Bitcoin came out, people realized they could sort of fork the code and make a small change or improvement. And some of them were kind of trivial. You know, like I think Litecoin sort of like changed the block size parameter and maybe the proof of work like in a little bit, but it's kind of similar to Bitcoin. Some of them were a little more novel, like Monero, for example, added privacy. And then you had Dogecoin, which is a lot like Bitcoin, except, you know, the meme power. Bitcoin doesn't have a dog on it, so I don't know however it's ever going to win. Just kidding. Okay, and then finally, or not finally, but like next, Ethereum. So Ethereum is really what starts getting interesting. This is where we realize like, ooh, we can generalize this Bitcoin thing. So Bitcoin helps us track a shared history. Ethereum says, let's not just be a simple currency. Let's put a really rich state machine on top of this. Let's track an arbitrarily complex Turing complete state machine. So it's quite a step up in complexity that way, but it's also a big step up in like expressibility and what kinds of things you can build on it. You could never build anything like a social media platform on, I shouldn't say never, but like it would be very hard to build like a social media platform on Bitcoin, and on Ethereum, it's a little easier to do that. It's at least certainly technically possible. The costs is a different question. Ethereum is unlike Bitcoin because it doesn't use that UTXO model where you're spending coins like we said. It actually uses a different model called accounts. I have a lecture tomorrow that explains the differences in detail, so you'll get them then. And like, the really crazy thing about Ethereum is that it's not just a single state machine, it's actually a virtual machine, and each contract or each individual state machine that runs on it can have its own internal state. So Ethereum VM is actually like a state machine whose job is to manage other state machines. Very inception-y. That's going to probably be useful in the contracts module. Okay, last slide, guys. Guess what? We made it. I can feel we're all getting a little low energy and ready for lunch. So the next one I'll say here are all sort of, these are like alt L1s, you can say, or an L0 if you like that narrative. And they're all sort of iterations on Ethereum in some way because they sort of do this general computing platform thing. You know, they're trying to be better than Ethereum in some way or another. For example, maybe interoperability or scalability or some different sexier consensus model. And by the end of this week, basically, by the end of this module, you should be able to pick any blockchain out of a hat, like maybe read its white paper or whatever, and then be able to categorize it like this. Like, what is its consensus? What is its state machines? What are its most unique value add? Like, does it use a typical blockchain data structure? Normally they do, but there's also a directed acyclic graph that I'll talk about a little bit later on. I think that's my last slide. Yeah, it is. Okay, and it's almost lunchtime, so I'm just going to wrap right here, and I guess we'll be back at 2. Thanks a lot, guys, for the first lecture. I really appreciate your attention.